Welcome back. Let's review the valuation of annuities. All right, so in this video, we are going to be reviewing the second unit of financial mathematics, at least the way that I have it broken up, or the way that I've decided to group the different concepts together in this course. And the second unit is all about how we value different types of annuities or series of payments. And so that's what we talked about in lessons 11 through 19 of my financial mathematics series. And so if you haven't watched these lessons, I do recommend that you do that first because this is a review video. I'm not going to be teaching you these concepts for the first time, but rather we are going to review them. And so this includes the future value of annuities, the present value of annuities, perpetuities, annuity immediate versus annuity due, continuous annuities, geometric annuities, arithmetic increasing annuities, arithmetic decreasing annuities, and increasing perpetuities. Those are all the topics that are included in this second unit that we are going to review in this video. Okay, now similar to my Unit 1 review, the way that I'm going to go about things here is to first review all the different formulas that you want to know regarding the valuation of annuities or regarding Unit 2, and then after we quickly review all those formulas, we will move into our example problems or our review problems. And so let's not waste any more time. Let's do a quick recap of all the formulas you want to know for the valuation of annuities. All right, so first up, we want to look at the formulas for level payment annuity immediates. These are your very basic annuities, the first type of annuity that you encounter. If you want to calculate the present value of an annuity immediate, you use this notation, which is equal to this formula. We have a n bracket I, which is equal to 1 minus a present value factor to the power of n divided by I. Now, of course, n is the number of periods for that annuity or the number of payments. I is the interest rate for that annuity, and it's important that that interest rate matches the payment cycle. And what I mean by that is if the payments of the annuity that you want to calculate the present value of, if those payments are being made yearly, then you better be using a yearly interest rate or an annual interest rate. In the same way, if the payments were being made monthly, then you would want an effective monthly interest rate. Okay, so it's very important that that interest rate is an effective interest rate that matches the payment cycle. But then if you want to calculate the future value of a level payment annuity immediate, this is the notation that you will use. We have S n bracket I. Again, n is the number of payments, I is the effective interest rate that matches the payment cycle, and that's equal to 1 plus I to the power of n, an accumulation factor to the power of n, minus 1 divided by I. All right, now for both of these formulas, or both of these notations, for present value and future value, you want to multiply those notations by the amount of each level payment. All right, so if you have a series of level payments of $100 every year, then you would multiply these notations by 100 to either calculate the present value or the future value. All right, and then a couple side notes here. There are some relationships that you should be aware of between these two formulas or these two notations. You can calculate the future value of an annuity immediate by taking the present value of that same annuity immediate and accumulating it for an n number of periods. All right, in other words, you are taking the present value forward in time to where the future value would be valued. Okay, you're accumulating that present value for an n number of periods. That will give you the future value. And so then the reverse is also true. You can calculate the present value by taking the future value backward in time by multiplying by a present value factor to the power of n. Okay, so these two relationships are true for these formulas, and you're going to find that very similar relationships are true for all of our other annuity formulas as well. All right, but we'll talk about that more in a little bit. Let's move on to our next set of formulas. We just got done looking at level payment annuity immediates, but now we're looking at level payment annuity dues. Remember that the difference between an annuity immediate and an annuity due is when the payments are being made. For an annuity immediate, the payments are being made at the end of every period, but for an annuity due, the payments are being made at the beginning of every period. That's really the only difference, but because of that difference, the way we value an annuity immediate and an annuity due is slightly different. Okay, so for the present value of an annuity due, we have this notation. It's the same as a level payment annuity immediate, except now we add these little dots above the A, and the same thing will happen for the S notation, but we have A double dot N bracket I, which is equal to 1 minus v to the power of n divided by 1 minus v. But if you remember from Unit 1, 1 minus v is also equal to an effective discount rate, the equivalent effective discount rate. So you could also rewrite this formula like this, 1 minus v to the power of n divided by d. All right, but then to calculate the future value of a level payment annuity due, the notation is s double dot n bracket I, and that's equal to 1 plus I to the power of n minus 1 divided by 1 minus v, which once again you can replace that with d, and this would be another way to write that formula, where of course d is an equivalent effective discount rate for your effective interest rate that you would be using for that calculation. Okay, now once again, just like with level payment annuity immediates, the interest rate that you use should match the payment cycle. If you have annual payments, you should have an annual effective interest rate. If you have quarterly payments, you should have a quarterly effective interest rate, and so on. All right, that always needs to be true. And also, like level payment annuity immediates, you multiply these notations by the amount of the level payments. So if you have payments of $500 every period, you want to multiply these notations or these formulas by 500 in order to calculate the present value or future value of those payments. Okay, and if I didn't mention it, n of course is still the number of payments. That really doesn't change. N always represents the number of payments or the number of periods that you are working with. Okay, and then we have these relationships down here. They should look very familiar. It's basically the same thing we talked about with level payment annuity immediates. You can calculate the future value of an annuity due by taking the present value of that same annuity due and accumulating it for an n number of periods. And the reverse is also true. You can calculate the present value of an annuity due by taking the future value of an annuity due and bringing it back an n number of periods by multiplying it by a present value factor to the power of n. Okay, so those are the formulas and relationships to know regarding level payment annuity dues. But now before we move into our next set of formulas for a different type of annuity, just a quick side note on annuity immediate versus annuity due. Remember that I said that the only real difference between an annuity immediate and an annuity due is when the payments are being made, whether they're being made at the beginning or the end of every period. And so because of that, the calculations are very similar, but they are off by one period. What I mean by that is that the present value of an annuity due is actually just the present value of an annuity immediate brought forward one period, multiplying it by 1 plus I. Okay, so if all the information for an annuity due was used instead to calculate an annuity immediate, if you just brought that calculation forward one period, it would be the same thing. Okay, so this notation is equal to this notation times 1 plus I, or this formula is equal to this formula multiplied by 1 plus I. However you want to view it is fine, but this relationship is true, as is the case for a future value scenario. The future value of an annuity due is equal to the future value of an annuity immediate brought forward one period. You can multiply it by 1 plus I, and that will give you the same thing as this notation or this formula. All right, and this is very important to remember. This pattern is true for all annuity types, whether you're working with increasing annuities, decreasing annuities, perpetuities, whatever type of series of payments you are working with, the only difference between the immediate and due versions is a period of 1 year. Okay, you can always take the annuity immediate version, bring it forward 1 year to get the annuity due version. Okay, and I will probably continue to mention that a lot throughout this video. So if it's not sinking in yet, it will hopefully by the end of this video. But to summarize everything we talked about for annuity immediate versus annuity due, we can sort of group everything together with this chart. We have the present value formulas in this row, the future value formulas in this row, and then the annuity immediate formulas in this column, and the annuity due formulas in this column. You can get from the immediate formulas to the due formulas by multiplying by 1 plus I, and you can get from the present value formulas to the future value formulas by multiplying by 1 plus I to the power of n. Okay, so we already looked at these formulas. I'm not going to read through them again, but this chart sort of summarizes everything we know about annuity immediates versus annuity dues. But now let's move on to a different type of annuity. Next, let's talk about arithmetic increasing annuities. And if you don't remember what that is, an arithmetic increasing annuity is an annuity where the payments increase every period by a set amount. All right, so not a percentage, a set amount. So what that means is that you might have a series of payments where every payment increases by $100 or every payment increases by $1,000, right? Every single period, the payments are increasing by a set amount. All right, and so now looking at the formulas for an arithmetic increasing annuity, we have both immediate versions and due versions for both present value and future value scenarios. For the present value of an arithmetic increasing annuity immediate, this is the notation and the formula. We have IA and bracket I is equal to the present value of an annuity due, which is not wrong. I know that might seem weird because we're talking about an annuity immediate here, but that is right. That is what is inside this formula. We have that notation minus n times v to the power of n divided by I. Now, if you want to calculate the future value of an arithmetic increasing annuity, the formula changes. We have a slightly different notation. Instead of IA, we have IS, and then n bracket I is equal to the future value of an annuity due minus n divided by I. Now, the annuity due versions of those formulas have very similar notations. You just add the double dots above the A or the S, and then the formulas are basically the same, except the denominators change from I to 1 minus V. And once again, 1 minus V is the same as the equivalent effective discount rate. All right, so if you want to use that instead, you could, but typically I don't recommend that. I like to work with 1 minus V so I can just keep using the same interest rate throughout the whole formula. And once again, you can get from the immediate formulas to the due formulas by multiplying by 1 plus I, and you can get from the present value formulas to the future value formulas by multiplying by 1 plus I to the power of n. Okay, so those are the notations and formulas for arithmetic increasing annuities. Now let's look at arithmetic decreasing annuities. For arithmetic decreasing annuities, we also have immediate formulas and due formulas for both present value and future value scenarios. And before we take a look at them, arithmetic decreasing annuities are annuities where every payment decreases by a set amount. Okay, so every payment might decrease by $100 every period, or maybe every payment decreases by $1,000, whatever it may be, every single payment decreases by a set amount. But now for the present value of an arithmetic decreasing annuity immediate, this is the notation and formula. We have capital DA and then n bracket I is equal to n minus the present value of an annuity immediate divided by I, and then the future value of an arithmetic decreasing annuity immediate is represented by this notation, capital DS, n bracket I, and that's equal to n times 1 plus I to the power of n minus the future value of an annuity immediate divided by I. Okay, and then the due versions of those formulas, once again, they are very similar. All that's different is the denominators. Instead of I, we have 1 minus V, which once again could be rewritten as the equivalent effective discount rate. And then, of course, for the notations, we just add the double dots above the A or the S to signify that they are annuity due formulas. Okay, and you can always go from the immediate formulas to the due formulas by multiplying by 1 plus I, and you can go from a present value formula to a future value formula by multiplying by 1 plus I to the power of n. And so that's it for the formulas for arithmetic decreasing annuities. Now, before we move on to our next type of annuity, there is a little side note that I want to talk about regarding arithmetic increasing and decreasing annuities, and it has to do with how we use the formulas. For one thing, as I've said, remember that the payments increase or decrease by a set amount when dealing with arithmetic annuities. I think we already kind of covered that, but what I want to focus on now is how we use those notations or use those formulas. And note that this works for both present value and future value formulas, as well as both annuity immediate and annuity due for arithmetic annuities. I'm just using these two notations as examples. But when working with an arithmetic increasing annuity formula, the value of x, or the amount that you multiply by that formula, needs to be the amount of the first payment and the amount that every payment increases by. Okay, so if you multiply this formula by 100, 100 better be the amount of the initial payment and the amount that every payment increases by. If that's not the case, then you will have to make an adjustment. You will have to split up your payments into two sets of payments, where one will be an arithmetic increasing annuity and the other one will be a level payment annuity. And if you're not sure what I'm talking about, be sure to revisit my lesson and examples videos for arithmetic increasing annuities. Okay, I believe I show an example of where you would have to make an adjustment like that. But then on the flip side, for arithmetic decreasing annuity formulas or notations, the amount that you multiply needs to be the amount of the final payment or the last payment and the amount that every payment decreases by. If that's not the case, once again, you will have to make an adjustment. You will want to split up your payments into two sets of payments that you will value separately with appropriate formulas that you would then add together. Okay, if you're ever unsure if your setup is correct for an arithmetic decreasing annuity, what you can do is take x, the amount outside of the formula, and multiply it by n, the number of payments, and x times n should be equal to the amount of the first payment. Okay, if that's not true, then you know that you don't have it set up right. Okay, x times n for an arithmetic decreasing annuity should always be the amount of the first payment for the series of payments. So please keep this in mind when using the notations and formulas for arithmetic annuities. They work a little bit differently than your regular level payment annuities, so always make sure that these requirements are met when setting them up. All right, but moving on to our next type of annuity. Here we have continuous annuities that are being calculated with a constant force of interest. Remember that continuous annuities are annuities where the payments are being paid continuously, which is not something that we can practically do in the real world, but it is something that we can think about theoretically in terms of math. So even though making payments continuously doesn't really make sense, we can still calculate the present value or future value of said annuities. For the present value, the notation looks like the present value of an annuity immediate, except you draw a bar over the A. So we have A bar and bracket I, and that's equal to 1 minus v to the power of n divided by the constant force of interest. And I really want to stress that that force of interest would need to be constant, meaning that it's not dependent on time or it's not defined in terms of a variable t, right? If the force of interest is just 5%, or 0.05, whatever, if it is a constant value, then these are the formulas that you want to work with. Now for the future value case, the notation is S bar n bracket I, and it's equal to 1 plus I to the power of n minus 1 divided by that constant force of interest. Okay, and of course you can go from the present value formula to the future value formula by multiplying by 1 plus I to the power of n. Now, these formulas are very similar to our formulas for an annuity immediate and an annuity due, and so I have those relationships highlighted over here. Really all that's different is what is in the denominator of these formulas. So you can get the present value or future value of a continuous annuity by taking the corresponding formula for an annuity immediate and multiplying it by the interest rate divided by the force of interest. And you can do the same thing for the annuity due formulas, except of course in their denominators you have 1 minus v, so that's what you want to have in the numerator of what you're multiplying them by. Okay, multiplying these formulas by these fractions eliminates the 1 minus v in the denominator of their formulas and replaces it with the constant force of interest that you would want in that denominator. Okay, so these relationships are true. These are just some alternate ways of calculating a continuous annuity if you don't want to use these formulas, but really it's the same thing anyway. I just thought I would include these here so that you have some different options on how to calculate a continuous annuity when working with a constant force of interest. But what if that force of interest is not constant, right? What if you have a force of interest dependent on time? Well, we call that a variable force of interest. And so when you're working with continuous annuities that need to be calculated using a variable force of interest, you have slightly different formulas. You're going to have to use calculus. All right, for a future value scenario, we have the same notation, except we replace the interest rate with that force of interest delta t, and you'll see the same thing down here for the present value notation. But the future value of the continuous annuity is equal to the integral from 0 to n of exp, which just means the number e raised to the power of what is inside these parentheses. So we have e raised to the power of the integral from t to n of that variable force of interest delta t dt, and then dt for the outer integral. And whatever the payment amount is for the continuous annuity, you would also multiply by this notation and include it in this integral. Okay, but then to calculate the present value of a continuous annuity with a variable force of interest, you have the integral from 0 to n of e raised to the power of this expression, the negative integral from 0 to t of the force of interest delta t dt, and then dt for the outer integral. Once again, whatever the payment amount is, you would multiply by this notation and include it in the integral. Okay, probably not your favorite formulas. A lot of us don't really get too excited about doing calculus in financial mathematics, but it is a thing that happens. It is a thing that you may have to do from time to time. So you have to know these formulas and you have to know how to integrate. Okay, but moving on, don't forget about geometric annuities, which are different from arithmetic annuities. You have a geometric annuity when the payments increase or decrease by a percentage, and we call that percentage an inflation rate. Okay, so that could be that every payment increases by 3% every period, or it decreases by 3% every period. When your payments increase or decrease every period by a percentage, you are working with a geometric annuity. Now, unlike some other resources out there, I do not recommend that you use a formula for geometric annuities. I don't give you formulas for geometric annuities because geometric annuities are more of a case-by-case thing. There are formulas out there that you can use, but they are very case specific. And a lot of the times in problems for financial mathematics, geometric annuities aren't always structured the same way. They're not cookie cutter problems, and so formulas are not very helpful. Instead, what I teach in my lesson on geometric annuities is to use this 4-step process of first valuing each payment at the valuation date using present value and accumulation factors. Then you want to factor out the first term from those series of terms that you wrote in step 1, and then you want to rewrite the remaining factor as a sum or a geometric series. And then from there, you can compute the sum of that geometric series, multiply it by that first term that you factored out, and that's how you compute the geometric annuity. It sounds like a lot of work, but once you do it a couple of times, you kind of get to see the pattern of how this sort of works out. And over time, geometric annuities won't be as intimidating. I know it can be a little bit scary to not have a formula for these type of annuities, but trust me, you're more likely to get the right answer using this 4-step process than trying to use a formula for this type of annuity. Okay, now moving on. We can't forget about perpetuities, which are annuities that go on forever. They never stop making payments. And so because of that, we really only look at the present value of perpetuities. It doesn't really make sense to calculate the future value because where would you value the future value? The payments go on forever. There's never an end date, so the future value doesn't really make sense to look at. So we're only worried about present values when talking about perpetuities. And so if you want to calculate the present value of a perpetuity immediate, the formula is very simple. It's 1 divided by I. Okay, and notice that in the notation here, we don't really use this that often, but notice that the number of payments n is infinity because it goes on forever. That formula just turns out to be 1 divided by I, and so whatever the payment amount is for a level payment perpetuity, you could multiply that by this expression, and so really you would have the amount of the level payments divided by I. Okay, if you want the present value of a perpetuity due, you can just multiply this by 1 plus I. That's what I do. I take 1 divided by I and multiply it by 1 plus I. But another way that you could write it is 1 divided by 1 minus V, which would be the same as 1 divided by the equivalent effective discount rate. Okay, so those are for level payment perpetuities, but some perpetuities will have payments that increase over time. And so we refer to those as increasing perpetuities. We don't really talk about decreasing perpetuities because you can't really decrease the amount of payments forever. At some point, the payments are going to become 0 and you're not making payments anymore. So it doesn't really make sense to talk about decreasing perpetuities because you can't decrease the amount forever, but you certainly can increase the amount forever. So we are interested in increasing perpetuities only. Okay, but now if the payments are increasing with an arithmetic progression, meaning that they are increasing by a set amount, this is the formula you want to know. You have p divided by I plus x divided by I squared, where p is the initial payment and x is the amount by which each payment increases. Now, it may be the case that p and x are the same, but they're not always, and so you want to make sure to identify both the initial payment and the amount that each payment increases by. Okay, now this is of course for an arithmetic increasing perpetuity immediate. If you want the due version, I would just multiply this formula by 1 plus I. All right, just multiply both of these terms by 1 plus I. Don't memorize another formula. This is all you need to do to calculate the due version. All right, just remember that the interest rate that you use in either formula should match the payment cycle. If you have annual payments, use an effective annual interest rate. Okay, and then we have geometric increasing perpetuities. which is where the payments would increase by a percentage every period. Very similar to how we have a 4-step process for regular geometric annuities. For geometric perpetuities, we have a 2-step process of valuing each payment at the valuation date, using present value and accumulation factors, and then you just use this formula. Whatever the first term is, you divide it by 1 minus 1 plus r divided by 1 plus I, where r is the inflation rate, or the percent that every payment increases by, and I, of course, is the interest rate. Okay, and so with that, that is it for increasing perpetuities, and it's also the last formula that I wanted to review for this unit. I know that was a lot. I know we spent a lot of time on formulas here, but it is important that you know these formulas. We're not going to be able to solve a lot of the problems for this unit, and honestly beyond this unit in financial mathematics. Being able to value annuities is extremely important, and so you want to be aware of all these different formulas, how they work, when to use them, and how they are related to one another. And by the way, we're not going to use all the formulas we just went over in this video in our example problems. We will use a bunch of them, but we're not going to use all of them. But that does not mean that you do not need to know all of them, because you may need to use some of the ones we don't use in this video for other types of problems you might see in financial mathematics. Okay, so I just wanted to make that clear before we move any further. And so now that we have reviewed all the different formulas for this second unit, now let's finally get into our example problems, or the review problems for this unit. All right, let's take a look at the first one. Okay, so here's example 1. Before we get started, I just want to say this. Since this is a unit review video, if you want to test your knowledge on the valuation of annuities, I would encourage you to pause this video at the beginning of every review problem. I would pause the video, try the problem out for yourself, see if you can solve it on your own, and then once you get the answer, or if you get stuck or something, then feel free to play the video and see how I go through the example and compare your work to mine, okay? I think that's going to be very beneficial if you are preparing for a quiz or an exam. Don't just watch me do the work, try to do a little bit of it yourself, okay? I think that will help you retain the information better and ultimately learn something from this video, okay? Obviously, it's really up to you how you want to use this video. You don't have to do that. If you just want to sit back and relax and watch me, that is fine too, but I do recommend that you try these problems for yourself. Okay, but now putting that aside, let's take a look at example 1 here. We want to find the value of the following, and we have 5 different annuity notations set up for us that we want to value. Okay, so this problem is testing your knowledge of annuity formulas, or can you value these different annuities? Okay, now if you are fluent with a financial calculator, such as the BA2 Plus from Texas Instruments, these are probably really easy calculations you can do very quickly in that calculator, but I'm not going to do that in this video. I really want to focus on what the actual formulas are for these notations, so even though you could definitely calculate these annuities really quickly in a financial calculator, I am still going to write out the formulas in this case because it is important that you do know those as well. Okay, but let's start with part A. Let's calculate the value of this annuity. We're calculating the future value of an annuity immediate with 30 payments and a 7% interest rate. Now, there's nothing being multiplied by any of these notations, so what that means is that the amount of every payment is $1. Okay, so just keep that in mind. But for part A, S30 bracket 0.07 will be equal to 1.07 to the power of 30 minus 1 divided by 0.07, right? It's an accumulation factor of 1 plus the interest rate to the power of n minus 1 divided by the interest rate, okay? That is the formula that corresponds to this notation. And so if you plug that into your calculator, you will get that the future value is equal to $94.46. That is the value of that annuity. Now let's move on to part B. We now have the present value of an annuity immediate with 30 payments of $1 using a 7% interest rate. That formula looks like this. First, I'll write the notation down again. We have A30 bracket 0.07. That is equal to 1 minus a present value factor to the power of n, which in this case is 30. And I'm just going to write the present value factor to be what it's actually equal to, which is 1 divided by 1 plus the interest rate. So we have 1.07 to the power of 30. And then we're dividing by the interest rate, 0.07, okay? And if you plug that into your calculator, you will find that the present value is equal to $12.41, okay? Moving on to part C, we have the future value of an annuity due, and we know it's an annuity due because of the double dots above the S. And so let's do that next. For part C, we have S double dot 30 bracket 0.07. The formula is the same as the formula for an annuity immediate, except the denominator will be a little bit different. Instead of just the interest rate, we'll have 1 minus a present value factor to the power of 1. So this is going to be equal to 1.07 to the power of 30 minus 1 divided by 1 minus 1 divided by 1.07, right? That is a present value factor to the first power. It's 1 divided by 1 plus the interest rate. So if you plug this into your calculator, you will find that that future value is equal to $101.07. Okay, that is the answer for part C. Now let's move on to part D. For part D, we have the present value of a continuous annuity with 30 payments of $1 using an interest rate of 7%. The reason I know it's a continuous annuity is because of the bar above the A. That's how we denote a continuous annuity. So the formula will look a little bit different. For part D, we have A bar 30 bracket 0.07. That will be equal to 1 minus a present value factor to the power of n, which is 30. But once again, I'm going to rewrite what that would actually be, which is 1 divided by 1.07 to the power of 30. And then that is divided by the force of interest. And we don't know what that is, right? What is the force of interest in this case? Well, we don't know, but we do know the effective interest rate, and we're going to assume here that that is an annual effective interest rate. And so what we can do here is remember that a constant force of interest is equal to the natural log of 1 plus I, the annual effective interest rate. So we can just replace delta with the natural log of 1 plus I. That's what I'm going to do here. I'm going to rewrite delta as the natural log of 1 plus I, but now I is 0.07, so we'll have 1.07. Okay, that's just the conversion formula from Unit 1 for converting between an annual effective interest rate and a constant force of interest. But now, plugging all this into your calculator, 1 minus this present value factor divided by the natural log of 1.07 will give you a final answer that the present value of this continuous annuity is $12.84. Okay, now let's move on to our last calculation here. We want to value this perpetuity with payments of $1 forever using an interest rate of 0.07. This is probably the easiest one to calculate. For part E, we're calculating the present value of a perpetuity, which is just going to be equal to 1 divided by the interest rate, so 1 divided by 0.07, which is equal to 14.29. That is the present value of that perpetuity. Okay, and so that's it for this example. Hopefully this served as a nice little review on what these formulas are equal to and how to use them. Now let's move on to our next problem. For example 2, we have a loan of $9,000 is to be repaid with 5 level year-end payments at a quarterly effective interest rate of 2.5%. What is the annual payment? Okay, so before I get started here, take this opportunity to pause the video and try this problem for yourself, see what type of answer you get, and then play the video to see what I do. But now I am going to get started here. The first thing I notice in this problem is that we are very clearly working with an annuity, right? We have a loan that is going to be repaid with 5 level year-end payments. We have a series of payments, so it's very clear here that we are working with an annuity of some kind. Now, when working with annuities, it is important that you can identify whether we are working with a present value or a future value scenario. And so what are we working with in this case? Well, it's going to be a present value. We have a loan of $9,000. Whenever you are talking about a loan or a debt or anything that you are taking out today, right? When you take out a loan, you take it out immediately, you take it out today, you get that money now, and you're repaying it, you're paying it off over time. That loan amount or that debt is always valued at time 0, so it's a present value. All right, so what we know in this case is that $9,000 is the present value of our annuity. It's going to be equal to the present value of our 5 level year-end payments, which, by the way, what does that mean? 5 level year-end payments? Well, what that's telling us is that we have an annuity immediate. The payments are being made at the end of every year. And so it's an annuity immediate, not an annuity due. So our notation would look like this. We have A5 bracket And then we'll have to talk about the interest rate. I'll get to that in a second. But this is our initial setup for the present value of those payments, which we know is going to be $9,000. But as you can see, in this problem, we don't know what the actual payment amount is, right? We want to know what is the annual payment. That's what's going to go right here, the unknown payment amount that I'm going to represent with X. Okay, we would be taking the present value of 5 of those payments of X, which are level payments, and that present value should be the amount of the loan, $9,000. Now, there's one more thing we have to deal with here, and that is what type of interest rate are we working with here? Well, we're given a quarterly effective interest rate of 2.5%, and this is where a lot of people will make a mistake. They will go right to this. They'll say, oh, the interest rate is 2.5%, so we'll have 0.025, but that's wrong. Remember what I said earlier in this video when we were reviewing our formulas. The interest rate for your annuity formula needs to match the payment cycle. And in this case, our payments are being made every year, right? We have 5 level year-end payments, but this is not a yearly interest rate. It's a quarterly effective interest rate, so we can't use that in this formula. We have to convert it to an annual effective interest rate. Okay, so what we've been given here is a quarterly effective interest rate of 2.5%. So that's a quarterly rate J sub 4, a non-annual effective interest rate that would take place 4 times in a year because there's 4 quarters in a year. We know that that's equal to 0.025. So let's convert that to an annual effective interest rate. I is going to be equal to 1.025 to the power of 4 minus 1. Hopefully this should look familiar. This is something that you learned how to do in Unit 1. If you don't remember that, be sure to go back and review your interest rate conversions. But if you perform this calculation in your calculator, you will find that the annual effective interest rate is equal to 0.1038 and some more decimals. I'm going to cut it off there. 10.38% is good enough. We can then use that interest rate for this annuity because now we have an annual effective interest rate. So we have 0.1038. Just try to use as many decimals as you can when you actually go through with this calculation, because now what we want to do is solve for X here. That's the amount of the annual payment that we want to find. And once again, just like with example 1, if you were good with a financial calculator, this is a very quick calculation that could be done in a financial calculator, but I'm not going to use one in this video. I just want to show you the actual math, the actual algebra that's taking place. It's ultimately up to you whether you want to do it this way or if you want to be more efficient and use a calculator to do these calculations quicker. Okay, obviously in the long run, it's going to be better if you can use a financial calculator, but in the beginning here, when you are first learning about the valuation of annuities, I think it's important that you write out what these notations are equal to so you get those formulas ingrained into your brain, because sometimes you will still have to pull them out. Your calculator can't do everything. All right, but here's what we're going to have here. We'll have 9,000 is equal to X times this formula, which will be equal to 1 minus a present value factor to the power 5, but I'm going to rewrite that to be what it would actually be equal to, which is 1 divided by 1 plus the interest rate to the power 5, so we'll have 1.1038 to the power 5, and remember to try to keep as many decimals as you can there. I'm just going to cut it off at 4 decimal places to keep things simple, but when you actually do the calculation, try to include as many as possible. But all that is then divided by that interest rate, so we have 0.1038. Okay, now if you plug this part into your calculator, it's approximately equal to 3.75. So what we get here is 9,000 is equal to X times 3.75 and some more decimals. Then to solve for X, you divide both sides by 3.75, and that will give you that X is equal to $2,397.35. Okay, that is the final answer to this problem. This $9,000 loan would be repaid with 5 level year-end payments of this amount if we had a quarterly effective interest rate of 2.5%, which is equivalent to an annual effective interest rate of 10.38%. All right, let's move on to our next problem. For example 3, we have that you want to accumulate $15,000 in an account earning an annual effective discount rate of 5% by making level deposits at the beginning of each of the next 11 years. Find the required level payment. Okay, so once again, if you want to try this problem out for yourself first, be sure to pause the video now. But if you want to see the solution, then let's get right to it here. Once again, we are working with some kind of annuity. Notice that in this case, we are making level deposits or payments at the beginning of each of the next 11 years. All right, so we have a series of 11 payments or 11 deposits. So that is an annuity, and they are taking place at the beginning of each of those next 11 years or at the beginning of every period. So that means that we are working with an annuity due, not an annuity immediate. All right, now in order to actually set anything up here, are we working with a present value or a future value for this annuity? Well, we're working with a future value. And here's why. We want to accumulate $15,000 in an account by making these deposits at the end of the next 11 years. Whenever you are talking about an accumulation or a total accumulated value at the end of a certain amount of time, that's a future value. We want to accumulate this amount. We don't already have it. If we already had it, that would be a present value at time zero, but we don't have it. We want to accumulate the $15,000, so it's a future value. So that $15,000 is our future value, and it's going to be equal to the future value of our series of payments. Now, in this case, we don't know the amount of the level payments or the level deposits, so I'm going to represent that with X again, but we would take the future value of those 11 payments using the future value formula for an annuity due, because those deposits are being made at the beginning of each year. All right, so we would have S double dot 11 bracket and then our interest rate, which we'll talk about in a second, but this is the setup so far. We have 11 payments of X at the beginning of every period that we want to take the future value of. So this is our formula for the future value of an annuity due. But what would our interest rate be? We're given an annual effective discount rate of 5%, but can we use a discount rate in this formula? Well, you could, but you'd have to make a lot of changes to the formula, which we don't want to do in this case. These formulas, the way that I presented them to you, are always assuming that you are working with an effective interest rate, not a discount rate. So we will have to convert our rate here. All right, we've been given an annual effective discount rate of 5%. So we were given that D is equal to 0.05, but we can't use that in this notation or in this formula. So let's convert this to an annual effective interest rate. The conversion looks like this. The annual effective interest rate is equal to D divided by 1 minus D, right? Hopefully that should look familiar from unit 1. So in this case, it's equal to 0.05 divided by 1 minus 0.05, which is equal to 0.05 divided by 0.95. And if you plug that into your calculator, you'll find that I is equal to 0.0526 and some more decimals. Okay, so that is the equivalent annual effective interest rate for our given annual effective discount rate. So now we can use that in this notation or in this formula because our payments are being made yearly, right? They're being made at the beginning of every year. So now we have an interest rate, not a discount rate, that matches that payment cycle. All right, so we have 0.0526 and some more decimals. Okay, now all that's left to do is to solve for the amount of the level payment X. So let's do that. We have 15,000 is equal to that amount X multiplied by this formula, which will be 1 plus that interest rate. So we have 1.0526 and some more decimals to the power of 11 minus 1 divided by what? Is it just the interest rate? No, because this is an annuity due formula, so the denominator will be 1 minus V, right? 1 minus a present value factor to the first power. However, something nice that happened in this case is we do know the discount rate, right? We have D equals 0.05. That's equivalent to 1 minus V. So we can save ourselves some trouble here and actually just put in 0.05. We can put that discount rate in the denominator there. Okay, you could write 1 minus the present value factor using that annual effective interest rate, but it might be a little bit more convenient in this case to use that effective discount rate. Okay, and so if you do this calculation in your calculator, it comes out to be about 15.16. So we'd have 15,000 is equal to X times 15.16 and some more decimals. And then if you divide both sides by this amount, that will solve for X. And so if you do that, you will find that X is equal to $989.33. That is the final answer to this problem. Okay, so 11 level payments of $989.33 made at the beginning of every year for those 11 years would accumulate $15,000, assuming that you had this annual effective discount rate, which is equivalent to this annual effective interest rate. Okay, let's move on to our next problem. All right, so for our fourth example, we have for I equals 0.045, find the following. And we have four different annuity calculations that we want to find. And so this is very similar to our first problem or our first example, except we are working with different annuity notations this time. Last time we were working with notations for level payment annuities, but now we have four different notations for arithmetic annuities, where the payments either increase or decrease by a set amount. Okay, so this problem is simply just testing your knowledge of the formulas for these notations. And so if you want to try this for yourself first, see if you remember the formulas for these different notations, be sure to pause the video and try to calculate these different annuities, and then you can play the video and see if you get the same answers that I do. All right, but let's start with part A. We have capital IA 10 bracket I. This is the notation for the present value of an arithmetic increasing annuity immediate. All right, and we have 10 payments and we're using an interest rate of I. Do notice that for all of these notations, we're not multiplying them by anything. So what that means is that we're technically multiplying them by 1. So in the case of this annuity, we have an arithmetic increasing annuity immediate with an initial payment of $1 that increases by $1 every period for a total of 10 payments. Okay, so here's what we'll have for part A. Our notation is IA 10 bracket I, but remember I is equal to 0.045, so we have 0.045, and that will be equal to the following formula. We have the present value of an annuity due with the same value of N and I minus N, which is 10, times V to the power of N, which is 10, or the present value factor to the power of 10. And then that's all divided by the interest rate, 0.045. Okay, now it might be helpful to write out what this notation is equal to as well. And so I'm going to write that here. The present value of an annuity due, which is what this represents, will be equal to 1 minus a present value factor to the power of 10, which in this case would be 1 divided by 1.045 to the power of 10. And then that's divided by 1 minus V, or a present value factor to the first power. So we have 1 divided by 1.045. Then we can subtract 10 multiplied by this present value factor, which would be 1 divided by 1.045 to the power of 10. And then that's all divided by 0.045. So not a very nice calculation. It's kind of ugly. And so this is where maybe using a calculator would be helpful. You could calculate this part in a financial calculator pretty quickly and then subtract 10 times v to the power of n and divide it by 0.045. But this is how you would write it out algebraically if you wanted to. And so however you like to go about these types of calculations is fine. But once you put this into a calculator, you will find that it's equal to $40.66. That is the present value of this arithmetic increasing annuity immediate. Okay, let's move on to our next annuity. Next up for part B, we have capital IS, 10 bracket I, which is the future value of an arithmetic increasing annuity immediate. So for part B, we have capital IS 10 bracket 0.045, and here's what that formula looks like. We have S double dot 10 bracket 0.045, the future value of an annuity due, using the same value of N and I, and then we subtract N, which is 10, and divide by the interest rate, 0.045. Okay, now let's rewrite this notation with its formula. Remember that this is the future value of an annuity due, so this will be equal to 1.045 to the power of 10 minus 1 divided by 1 minus a present value factor. So we have 1 divided by 1.045, and then we can subtract 10 and divide by 0.045. Okay, this right here is what this notation is equal to. All right, once again, a very complicated expression. It's not very nice, but if you do plug this into your calculator, what you'll find is that the future value of this arithmetic increasing annuity immediate is $63.14. All right, that is the value of this notation. Let's move on to part C. For part C, we have capital DA 10 bracket I. This is the notation that represents the present value of an arithmetic decreasing annuity immediate. We know it's decreasing because of the D. If it's D, it's decreasing. If it's I, it's increasing. So here's what we'll have for part C. Capital DA 10 bracket I, which is 0.045. Here's what that notation is equal to, or here's what the formula looks like. We'll have the value of n, which is 10, minus the present value of an annuity immediate with the same value of n and I. So we have a 10 bracket 0.045, and then we divide by the interest rate 0.045. Now if we write out the formula for this notation, this will be equal to 10 minus 1 minus the present value factor to the power of 10. So we have 1 divided by 1.045 to the power of 10 divided by 0.045, and then we divide all of that by 0.045. All right, so this right here is just the formula for that present value of an annuity immediate. But now if you plug all this into your calculator, you will find that the present value of this arithmetic decreasing annuity immediate is $46.38. Okay, now let's move on to our last annuity. Finally, we have part D with the annuity notation DS double dot 10 bracket I. This is the future value of an arithmetic decreasing annuity due. The double dots tell us that it's an annuity due, which is the only annuity due we've worked with so far. All the other annuities here were annuity immediates, but this one is an annuity due. So the denominator of the formula will be a little bit different. It won't just be the interest rate like it was in these three formulas. It will be 1 minus a present value factor to the first power. All right, so for part D, we have capital DS double dot 10 bracket I, which is 0.045, and that will be equal to the following formula. We have n, which is 10, times an accumulation factor, so we have 1.045, and that will be raised to the power of n, which is 10, and then we subtract the future value of an annuity immediate using the same values of n and I. So we have 10 bracket 0.045. And then all that is divided by 1 minus v, which will be 1 minus 1 divided by 1.045. Okay, now we do want to write out what this notation is equal to. It's the future value of an annuity immediate. So let's write all this out one more time. We have 10 times 1.045 to the power of 10 minus 1.045 to the power of 10 minus 1 divided by 0.045, and that will all be divided by 1 minus 1 divided by 1.045. Okay, so once again, another pretty complicated expression, but if you do put this into your calculator, here's what you'll get. The future value of this arithmetic decreasing annuity due is equal to $75.27. Okay, that is the value of that last annuity, and now we have completed this problem. Okay, so hopefully this is a good refresher on some of the formulas for our arithmetic increasing and decreasing annuity notations. But with that, let's move on to our fifth example problem. Hey there, real quick, before we move on to the next part of this video, if you are currently studying financial mathematics with the intent on taking the exam FM, then I want to give you a gift for watching this video today. I want to give you my free 6-week studying strategy guide for exam FM. Inside the PDF file, I lay out a reasonable studying timeline that you can follow to prepare for the exam FM in just 6 weeks using my own content as well as some other resources online. By all means, it is not the only way to prepare for the exam, but it can certainly help you get started. So if you're struggling to stay organized in your studying of FM topics or want an easy to follow schedule for preparing for your exam, then this guide is for you. And it's absolutely free. Just head on over to jkmathematics.com/studyfm 6 weeks. Once again, that's jkmathematics.com/studyfm 6 weeks. Or you can find the link in the description. Okay, now back to the video. Okay, so for example 5, we have Caroline makes monthly payments into an account paying an annual nominal rate of 6% convertible monthly. 1 month from today, she makes her first payment of $120 and then decreases the amount by 1% every month thereafter. If she makes these payments for 5 years, how much is in her account after her last payment? Okay, so if you don't want to see the solution yet, be sure to pause the video and try this out for yourself. see if you can solve this problem. But if you are ready to see me work through it, then let's do that. First thing I notice about this problem is that Caroline is making payments that decrease by a percentage every month. That is very clearly a geometric annuity. Whenever you have payments that are increasing or decreasing by a percentage, such as 1%, that's a geometric annuity. So it looks like we are calculating either the present value or the future value of a geometric annuity. Which one of those specifically are we doing is going to depend on how the question is worded. And in this case, the last sentence gives that away. If Caroline makes these payments for 5 years, how much is in her account after her last payment? All right, we're talking about an amount in the future. We want to know the value in her account after the last payment, which takes place in the future. So we're looking for the future value in this case. Now, how many payments is Caroline making? We know that she's making these payments for 5 years, but her payments are actually being made monthly, right? She makes monthly payments into an account paying an annual nominal rate of 6% convertible monthly. So her payments are being made monthly, which means that she's not just making 5 payments for 5 years, she's going to make 12 payments for each of those 5 years, which would be a total of 60, right? N is going to be equal to 12 payments for each of the 5 years in this problem. So that's a total of 60 payments or 60 periods. Okay, now her first payment is $120, and then from there on out, every single payment decreases by 1%, right? Every month thereafter, that decrease is taking place. So let's draw a timeline here. Let's visualize what's going on in this problem. This right here will be time equals 0, and this will be the last time for this problem, which is time equals 60, right? She's going to make a total of 60 payments, so we can end her timeline at time 60, okay? That would represent the 60th month. Every single period on this timeline is going to represent a month, since we are primarily working with months in this problem. The payments are being made monthly, and so that sort of takes priority here, okay? But then at time 1, Caroline makes a payment of $120, but then what about time 2? What would her payment amount look like? Well, it's going to be 1% less of $120, right? So how do we represent that? Well, let's just write down what that inflation rate is for a second. Her payments are decreasing by 1% every month. So the inflation rate R is equal to negative 0.01, right? We have a negative inflation rate because the payments are decreasing. So if you want to determine the amount of the next payment, what we usually do is we take our payment amount, in this case 120, and multiply it by 1 plus the inflation rate, which in this case, we would be adding negative 0.01, and 1 plus negative 0.01 will give you 0.99, right? Really what we're doing here is subtracting 0.01 from 1. So at year 2, the payment amount will be 120 times 0.99, okay? So that's what's going to go right here at time 2. We have 120 times 0.99. Then at time 3, how much will that payment be? Well, it's going to be the amount of the previous payment, but decreased by another 1%. So we just multiply it by another factor of 0.99. So we would get 120 times 0.99 squared. And so then at time 4, you would have 120 times 0.99 cubed, and that would continue on forever until the last payment. So let's skip some time here. Let's do time equals 58, time equals 59, and then there's time 60. So at time 58, our payment amount will be 120 times 0.99 to the power of 57, right? If the power of 0.99 was 2 when time equals 3, it's 1 less than the time. Then at time 58, the power will be 57, and that will continue on for the last 2 payments where we have 120 times 0.99 to the power of 58 and 120 times 0.99 to the power of 59. Okay. So I'm going to erase this work here. We don't need that. We have now drawn out a timeline that shows all of the payments that Caroline is going to be making, her monthly payments. And so if we want to calculate the future value, which by the way is going to be the amount in her account after her last payment, so immediately after the last payment would be at time 60, that's where we want to value everything. So I'm going to circle time 60. That's our valuation date. That's where we want to value everything. That's where the future value is valued. So that's what we want to calculate here. And so we can actually start our 4-step process now for calculating a geometric annuity. What we want to do is value all of these payments at the valuation date at time 60. So let's start with the first payment of $120. 120 is currently valued at time 1, but to value it at time 60, we need to bring it forward 59 periods, or 59 months. So we have 120 times 1 plus what? The interest rate, but what kind of interest rate do we need? Well, we'll come back to that. I'm going to leave that blank, but that will be to the power of 59. We want to accumulate that $120 for 59 months to value it at time 60. But now let's talk about the interest rate. What is that going to be? Well, this power 59, is representing a number of months. So our interest rate here that we need is an effective monthly interest rate. But what type of interest rate have we been given in this problem? Well, we have an annual nominal rate of 6% convertible monthly. So we've been given this. We know that the nominal rate convertible 12 times per year is 0.06. Thankfully, that is a nice interest rate that we can use to convert into a monthly effective interest rate, right? This is a nominal rate convertible 12 times per year. We can get the effective monthly interest rate by just dividing that by 12, all right? J sub 12, the monthly effective interest rate, would be equal to 0.06 divided by 12, which is equal to 0.005. All right, so that is what we want to use in this accumulation factor. We'll have 1 plus 0.005, which is 1.005. Okay, that is the monthly effective interest rate, so that's what our accumulation factors are going to look like when we value these different payments at time 60. Now, I'm obviously not going to write out all 60 terms, but I am going to write a couple more, and then we'll skip ahead to the last term. But if we value the payment at time 2 at time 60, we need to bring it forward 58 periods, or 58 months. So we'd have plus 120 times 0.99 accumulated for 58 months. So we have 1.005 to the power of 58. And then that would continue on from there. We could value the payment at time 3 at time 60 by bringing it forward 57 periods, or 57 months. And that would continue on until our last couple terms. That's what I'm going to skip ahead to now. I'm going to add plus plus our last term, which is already valued at time 60. So we just have to write 120 times 0.99 to the power of 59. Okay, so those are the terms that are going to represent the future value of this geometric annuity, or the value of it at time 60. That's step 1 of the 4-step process for valuing a geometric annuity. Now let's move into step 2, which is to pull out the first term. Right? You want to factor out the first term from all of the other terms. So if we do that, this will be equal to 120 times 1.005 to the power of 59. That's what we're going to pull out of all of those terms. So if we pull it out of the first one, we're just left with 1. But then for the second term, we pull out the 120. We pull out 1.005 to the power of 59, right? That's what we're pulling out. So that's going to leave this power to be negative 1. We're still going to have 0.99, but now that's going to be multiplied by 1.005 to the power of negative 1, right? If we're pulling out 59 of those factors, but we only have 58, we're going to be left with negative 1. All right, and then that will continue on to the last payment where we're pulling out that 120, so we're just going to be left with 0.99 to the power of 59, and then we're pulling out 1.005 to the power of 59, but we don't really have that here. So essentially what's going on is we're dividing this term by that factor. So you would have this factor in the denominator, or you could simply write it like this. You'll have 0.99 to the power of 59 times 1.005 to the power of negative 59. Okay, I hope that makes sense. We don't have any of those factors there. So if you're factoring out 59 of those factors, then you're going to be left with negative 59 of those factors. So now we've pulled out the first term out of all of the other terms. Now what we want to do is rewrite the remaining terms as a geometric series. So how's that going to work? Well, to maybe make it a little bit easier to see how we're going to do that, what I'm actually going to do is move these quantities with a negative exponent to the denominator of each of those terms. That way the power will be positive. So what we'll have here is 120 times 1.005 to the power of 59 times 1 plus 0.99 divided by 1.005 plus all the way up to 0.99 to the power of 59 divided by 1.005 to the power of 59. Okay, and so the pattern here is that every single one of these terms is just 0.99 divided by 1.005 to the power of 0, then 1, then 2, then 3, then 4, then 5, all the way up to the power of 59. So here's how we'd rewrite that as a geometric series. We'd have 120 times 1.005 to the power of 59 times the sum from k equals 0 to 59 of 0.99 divided by 1.005 to the power of k. All right, that represents the sum of these terms raised to a power of k, where you start with 0 and then you end with 59. Now what we can do is calculate the sum of this geometric series, and that will allow us to sort of finalize this calculation and be able to calculate the future value of this geometric annuity. So let's do that. If we calculate the sum of this geometric series, here's what we'll have next. This will all be equal to 120 times 1.005 to the power of 59 times 1 minus the expression inside a geometric series that's being raised to a power. So we'll have 0.99 divided by 1.005, and that will be raised to the power of the upper limit, which is 59, plus 1. So that would be 60. And then you're dividing by 1 minus that same expression, but not to the power of 60, just to the power of 1. So you have 0.99 divided by 1.005. Okay, just remember, I'll write it down here real quick if you want to reference it. Remember that the sum of a geometric series from k equals 0 to n of a raised to the power of k is equal to 1 minus a to the power of n plus 1 divided by 1 minus a. Okay, that's the formula that I used right here to calculate the sum of this geometric series. But now we have everything we need to calculate the future value of this geometric annuity. You can multiply 120 times 1.005 to the power of 59 by this rational expression. And if you do that, you will find that the future value is equal to $6,413.55. That is the future value of this geometric annuity that Caroline is making. All right, so that's it for this problem. Let's take a look at another one. Okay, so here's example 6. We want to find the force of interest at which S bar 40 bracket I is equal to 3 times S bar 20 bracket I. Or in other words, we want to find the force of interest at which the future value of a continuous annuity for 40 periods is equal to 3 times the future value of a continuous annuity for 20 periods where both annuities use the same interest rate. All right, now if you want to try this problem on your own first, now is the time to pause the video. But then once you're ready, I'm going to start working through it now. And it can be a little bit tricky to figure out where to start with this type of problem, right? We're not given a lot of information to go off of. We just know we want to find the force of interest at which this equation is true. And so since this equation has always been given, that's what we should work with, right? That's really our only option. So I'm going to write it down here. We have S bar 40 bracket I is equal to 3 times S bar 20 bracket I. Now, the only thing I can really think to do at this point is to simply write out what the formulas look like for these notations. And maybe that will help us get closer to finding this force of interest that we need to find. And so remember, the formula for the future value of a continuous annuity using a constant force of interest will look like this. We have 1 plus the interest rate to the power of n, which is 40, minus 1 divided by the constant force of interest, and that will be equal to 3 times 1 plus I to the power of 20. That's the value of n for this continuous annuity, and then we'll subtract 1 and divide by the force of interest. Now notice, on both sides of this equation, we have the constant force of interest in the denominator. So writing out these formulas for these notations now allows us to see something that we can cancel out, right? We can multiply both sides of the equation by delta, or the force of interest, and it will be gone. They are canceled out, okay? If you have the same factor on both sides of the equation, you can cross it out, you can cancel it out, and it makes for a nicer equation. So now, here's what we have. We have 1 plus I to the power of 40 minus 1 is equal to 3 times 1 plus I to the power of 20 minus 1. Okay, and now at this point, what are we going to do? Where do we go from here? Well, we know we want to find a force of interest, so probably our end goal here is going to be to first solve for I, this annual effective interest rate, and then convert it to a force of interest. Right, we're going to want to use this formula that the force of interest is equal to the natural log of 1 plus I. but in order to solve for delta, we of course need to know what I is. So how are we going to solve for I in this equation? It looks pretty complicated, and that I is inside a quantity to the power of 40 and a quantity to the power of 20, which is going to be really hard to get out of. Okay, and so if you tried this problem on your own, maybe this is where you got stuck. It's not entirely clear where we go from here, but here's what I'm going to do next, and then I'll talk about how we can simplify further. What I'm going to do is divide both sides of the equation by this quantity. So we'll have these two terms both divided by this, and that'll be equal to 3, all right? So I'm going to continue my work up here. If I divide both sides of the equation by this quantity, we'll have 1 plus I to the power of 40 minus 1 divided by 1 plus I to the power of 20 minus 1 equal to 3. All right, now here's where your knowledge of algebra is going to come into play. Because what do we have in the numerator and denominator right here of this expression? Well, we have two differences of squares, right? If you remember from algebra, if you have something like x squared minus 4, we called that a difference of squares because x squared is x squared and 4 is 2 squared. And when you have a difference of squares, you can factor it like this. You have x plus 2 times x minus 2, right? If we rewrite 4 as 2 squared, then you can see that factoring a difference of squares is as simple as writing two factors where you have x plus 2 and x minus 2. You have the first value that's being squared plus the second value that's being squared, and then you multiply by the first value being squared minus the second value being squared. So you have x plus 2 times x minus 2 is the same as x squared minus 2 squared, or x squared minus 4. We have the same thing going on here and here, although we're not going to want to factor both of them, because what we want to do is have something that cancels out, and factoring the numerator is what is going to allow us to cancel something out. Let me show you what I mean. We have 1 plus I to the power of 40 minus 1. This is a difference of squares. 1 squared is 1, and 1 plus I to the power of 40 could be rewritten as 1 plus I to the power of 20 squared, right? When you have a value raised to an exponent, you simplify that by multiplying the exponents. So 20 times 2 is 40. So you still have a power of 40, but now we're just viewing it a different way. We have 1 plus I to the power of 20 squared. So we really do have a difference of squares here. We have 1 plus I to the power of 20 squared minus 1 squared. So we could factor it like this. We'd have 1 plus I to the power of 20 plus 1 times 1 plus I to the power of 20 minus 1. All right, that's how we can rewrite this numerator. And so let's do that, and I think you'll see how that's going to help us solve for the interest rate. We have 1 plus I to the power of 20 plus 1 times 1 plus I to the power of 20 minus 1, and that's divided by 1 plus I to the power of 20 minus 1, and this is equal to 3. Look what we now have. We have this factor of 1 plus I to the power of 20 minus 1 in the numerator and denominator. They're going to cancel each other out. And so now what we're left with is just 1 plus I to the power of 20 plus 1 is equal to 3. And so if you subtract 1 from both sides of the equation, you get 1 plus I to the power of 20 is equal to 2, right? 3 minus 1 is 2. And then to solve for I, you just have to take the 20th root of both sides of the equation and subtract 1. So let's work on that. We'll have 1 plus I is equal to 2 to the power of 1/20th, right? We have to take the 20th root of both sides of the equation to get rid of that 20th power. And then if we subtract 1 from both sides of the equation, I'm just going to do that right now. We'll have 2 to the power of 1/20th minus 1. And plugging that into your calculator will give you that the annual effective interest rate is equal to 0.03526 and some more decimals. And now we have everything we need to get to the solution of this problem. We know that the force of interest is equal to the natural log of 1 plus I, and we now know what I is. So the force of interest is equal to the natural log of 1.03526 and some more decimals. Try to use as many as you can in this calculation to get as accurate of an answer as possible. All right, don't round off at 2.6. Try to include some more decimals if you can. But if you take the natural log of 1.03526 and some more decimals, you should find that the force of interest is equal to 0.0347 and some more decimals, or you could write that as 3.47%. Okay, that is the final answer to this problem. We have now found the force of interest for which this equation is true. If you have a force of interest of 3.47%, the future value of a continuous annuity for 40 periods is equal to 3 times the future value of a continuous annuity for 20 periods. Okay, let's move on to our next example. All right, so here's our 7th example. We have Brian makes deposits of $300 at the beginning of every year into an account earning a 10% annual effective interest rate. At the end of each year, he withdraws the earned interest and reinvests it into a different account earning a 15% annual effective interest rate. What is the combined accumulated value at the end of 10 years of Brian's two accounts? Okay, so once again, if you want to take a moment to pause the video and try this problem for yourself, now is the time to do so. But once you're ready to see me work through it, then feel free to play the video again, or if you don't want to pause the video, just watch me work through it now. And this is kind of an interesting problem because we're not just working with one account, right? Brian is making use of two different accounts, and he's doing two different things in each of those accounts. And so to keep things straight, what I'm going to do is draw a timeline for each account and then talk about what is happening in each of those accounts. All right, now in both cases, we're only looking at a period of 10 years because we want to know the combined accumulated value at the end of 10 years for Brian's two accounts. So that makes things simple from a timeline perspective. Let's draw two timelines here that both include a period of 10 years. So this will be time equals 0, and this is time equals 10, and this will be time equals 0, and this will be time equals 10. All right, this is going to be account 1, and this is going to be account 2. Now, in between there, we will have time 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I'll do that down here as well. We'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, now for the first account, Brian is making deposits of $300 at the beginning of every year. So let's write that in here. At the beginning of every year, so that means starting at time equals 0, because that would be the beginning of the first year, we're going to have $300 there, and then $300 at the beginning of every preceding year. All right, so we have $300 at the beginning of every year for 10 years. Okay, so that means we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 payments of $300. So we have the deposits of $300 at the beginning of every year, and it is important to notice that this account earns a 10% annual effective interest rate. So for this account, I equals 0.1. That's 10% as a decimal. But then notice what the problem tells us here. At the end of each year, he withdraws the earned interest and reinvests it into a different account earning a 15% annual effective interest rate. So that would be what our second account here is representing. That's where he's putting the interest. So let me just write down the interest rate real quick. We know that I is equal to 15% or 0.15 for this account. But what does it mean that he withdraws the earned interest and reinvests it into this account, into that different account, right? What does that mean? Well, let's take it case by case or year by year. Let's just look at the first year, right? After 1 year, not including the new deposit, $300 will be in his account, right? After 1 year, before he makes that new deposit, he will have $300. So the interest generated would be $300 times 0.1, right? So at year 1, the interest he earns is 300 times 0.1, which is $30. All right, so he earns $30 worth of interest in that first year. And according to the problem, at the end of each year, he withdraws any earned interest and reinvests it into the other account. So what that means is at the end of year 1, he's got $330, 300 plus the interest, but he takes out that interest and puts it into this account. So now we have $30 at time 1. Okay, and so now the interest that he generated is no longer still in this account, it's now down here. And so what that means is that at time 1, before he makes that new deposit, Brian is just left with $300. He took out that interest, so now all that's left in the original account is $300. But now he adds another $300 at time 1, so now after 2 years, he has $600 in the account. So the interest generated in that second year, So if we look at year 2, it will be 600 times the interest rate of 0.1, which is 60. So in year 2, he generates $60 worth of interest, but he's going to withdraw that and put it directly into the other account. All right, so at the end of 2 years, he takes out that interest earned and puts it into this account. So now there's $60 at time 2 in the other account. But now because he took out those $60, he took out the interest that was generated in this account, he still only has $600 at the end of those 2 years. So then at the beginning of the 3rd year, he adds another $300. So now he has $900 in the account. And so maybe now you can see the pattern. For year 3, he has $900. So the interest generated for year 3 will be 900 times 0.1, which is 90. And he's going to take that interest out and reinvest it into this other account. And so now hopefully the pattern is very clear here. With every year that passes, since Brian is depositing another $300, the interest generated is going to increase by $30. And since he's taking out the interest every single time, it's not compounding like it usually would. He's basically starting from scratch in this account every time when it comes to generating interest. In this account, we just have $300 being made every period, but every time interest is generated, he takes it out at the end of every year and puts it into this other account. So you're going to have payments of 30, 60, 90, 120, 150, 180, 210, 240, 270, and 300. Okay? And that should make sense because at the end of 10 years, he's going to have 10 payments of $300 in his account, which would be $3,000, right? That's how much is in his account at time 10. So for year 10, 10% of $3,000 would be $300. So that would be his interest amount that he would be withdrawing and depositing into this other account. All right, so I'm going to erase this work now. We now have 2 timelines that represent both of Brian's accounts. Now what we want to do is calculate the combined accumulated value at the end of 10 years for Brian's 2 accounts. All right, in other words, we want to calculate the future value at time 10 for both of these accounts and add them together. And so let's start with the first account. What is the future value of the account at time 10? You might be tempted to say, okay, well, the future value is going to be equal to 300 S double dot 10 bracket 0.1, right? It's the future value of an annuity due because the payments are being made at the beginning of each period. We have 10 of those payments and they are each of $300 and we're using a 10% interest rate. However, this is not correct in this case. Remember that Brian withdrew all of his earned interest. So this calculation would not be correct because this assumes that we are compounding the interest every single period. We're leaving it in the account as he makes those deposits of $300. That's not what's happening. All the interest that Brian earns is being moved into this other account. So this is not right. What the future value actually ends up being is just the sum of all of these deposits that he makes. It's $3,000. He makes 10 payments of $300. So the future value of account 1 is just 300 times 10, which is 3,000, because he took out all the interest that he earned. It's all in this other account. So at the end of 10 years, all that's left in account 1 is those deposits of $300 that he made over those 10 years. All right, so that's simple enough, but what about account 2? Well, account 2 has its own interest rate, and he's not withdrawing the interest this time, right? He's leaving the interest in this account, and I'm talking about new interest here, not these interest payments that he's depositing in. I'm talking about the interest that is going to be generated by these interest payments, right? That's staying in the account, so we can actually use an annuity formula for this account, unlike this one. Okay, I hope that makes sense. But now, what type of annuity are we working with here in this second account? Well, notice that we start with a payment of $30, and then every payment after that increases by $30 for 10 periods. So what we have here is an arithmetic increasing annuity immediate, right? The first payment takes place at the end of the first year, and then every payment after that increases by the same amount as that initial payment. So here's how we can calculate the future value of account 2. The future value will be equal to 30 times IS 10 bracket 0.15. This is the notation for calculating the future value of an arithmetic increasing annuity immediate. In this case, we have 10 payments using a 15% interest rate and the first payment is $30 and increases by $30 every period. So this is the right way to represent the future value of these payments. So writing out the formula for this notation will give us that this is equal to 30 times S double dot 10 bracket 0.15 minus N, which is 10, divided by I, which is 0.15, but then we have to write out what this annuity due notation would be equal to. So let's do that. This would be equal to 30 times 1 plus the interest rate. So we have 1.15 to the power of n, which is 10, minus 1 divided by 1 minus v, which is 1 minus 1.15 to the power of negative 1. You could write 1 divided by 1.15, but to save space, I'm just going to write it to the power of negative 1. Then you have minus 10 divided by 0.15. Sorry that my work is a little bit cramped there. Not exactly the best way to write that. I'll clean it up in a second. But now what you want to do is put this into your calculator and find the future value of that second account. And if you do that, here's what you'll get. You'll find that the future value of the second account is equal to $2,669.86. All right, that's the future value at time 10 of those payments in the second account. So if we want to know the combined accumulated value at the end of 10 years of Brian's two accounts, what we have to do is add our two future values together, or the two accumulated amounts for the two accounts. We'll have the total future value, or the combined future value, is equal to the future value of account 1, I'll just label it like that, plus the future value of account 2. And if you do that, you will find that it's equal to 5,669.86. Okay, it's just adding 3,000 to this number right here. All right, and that's it for this example problem. We have now found the combined accumulated value at the end of 10 years of Brian's two accounts. It was kind of a weird problem. It dealt with reinvesting interest into another account, but we were able to make sense of it by drawing some timelines to see where the payments were being made and where the interest was going, and it helped us kind of form a strategy on how to calculate this future value. Okay, and so with that, let's move on to our last example problem for this Unit 2 review. All right, so here's our 8th example problem. This is also the last example problem for this Unit 2 review. We have a perpetuity costs $104.92 and makes payments at the end of each year. The perpetuity pays $1 at the end of year 2, $2 at the end of year 3, and then that continues on until we have n dollars at the end of year n plus 1. After year n plus 1, the payments remain constant at n dollars. If the annual effective interest rate is 9%, find n. Okay, so now before I get started on the solution to this problem, if you want to challenge yourself, be sure to pause the video now and try this problem out for yourself. See if you can solve for n. All right, but now I'm going to get into the solution here. The first thing I want to point out here is that we are working with a perpetuity, and remember that that is an annuity that makes payments forever. The payments never end, and we know it costs $104.92. That would be the present value of the perpetuity. Whenever you're given a cost or a price of an annuity of any kind, including a perpetuity, that's referring to a present value, the value at time 0 today. All right, so that's something to keep in mind. That is the cost of the perpetuity. I'll label that as the present value. But then what do the payments look like for this perpetuity? Well, we're told that the perpetuity pays $1 at the end of year 2, $2 at the end of year 3, and that continues that pattern of increasing by $1 up until n dollars at year n plus 1. So it looks like we have a perpetuity that has an arithmetic increasing progression. However, that does not continue on forever, right? It says after year n plus 1, the payments remain constant at n dollars. So this is not an arithmetic increasing perpetuity that has payments that increase forever. It has payments that start to increase, but then at some point they level off and stay the same forevermore. So let's try to visualize that. Let's draw a timeline here, and that will help us make sense of what this perpetuity actually looks like in terms of the payments and where they are valued. and then we can begin to sort of talk about how we might solve for that value of n. All right, so here's my timeline. It does go on forever, and so there's really no end date, but we do have a beginning date of time equals 0. And where would the first payment of the perpetuity be? Well, we know that the perpetuity pays $1 at the end of year 2. That is the time of the first payment. So we have year 1, t equals 1, and then year 2, t equals 2. At the end of that second year, at time equals 2, there is a payment of $1. All right, so I'll put $1 at time 2. And then after that, we have $2 at the end of year 3. So if I write in time equals 3, then we'll have $2 at that time. And this pattern is going to continue. We're going to have an increase in $1 for each payment up until time n plus 1. So let me draw in a couple more here. Let's do time equals 4. We'll have a payment of $3, and at time equals 5, we have a payment of $4. All right, now that pattern will continue on, so I'm going to skip ahead until we get to time t equals n, and then t equals n plus 1. All right, now at t equals n plus 1, we have a payment of n, so I'll write in n, which means that the previous payment at time n will be n minus 1. Right? Whatever this payment amount is at t equals n plus 1, the previous payment should be $1 less, so it would be n minus 1. Okay? Now, after t equals n plus 1, the payments remain constant at n dollars. So let's draw in a couple more dates here. We'll have t equals n plus 2, t equals n plus 3, and that'll be good enough. We'll have n, and so on. Okay, so now we have a timeline that represents our scenario here. This helps us visualize the payments for this perpetuity. Now, one more thing that we could put in this timeline is the value of the present value of the perpetuity, which is $104.92. We could put that at time 0. So I'll do that here. We have 104.92. And so that present value should be equal to all of these payments valued at time 0. And really, this is all we know about this problem besides the interest rate. We know that the interest rate is an annual effective interest rate of 9%. So we know that I is equal to 0.09 as a decimal. But really, this is all we know about this scenario. So if we're going to try to solve for n, most likely what we will have to do here is set up an equation that would calculate this present value, right? Just set up an equation that sets this present value equal to all of these payments valued at time equals 0, and then see if we can solve for n in that equation, because it's going to involve n, right? That value of n is found in the payment amounts here, and it's also found in some of these later times. And so how are we going to do this? How are we going to value the present value of a perpetuity where the payments increase arithmetically, but then are level? They don't continue to increase forever like you might expect. In other words, what I'm saying here is that we're not going to be able to use this formula of p divided by I plus x divided by I squared, right? This is the formula that we use to calculate the present value of an arithmetic increasing perpetuity immediate. But that's assuming that the initial payment is p and every single payment increases by an amount x. But not every single payment is increasing for this perpetuity, right? They're only increasing up to a certain point. So here's what we're going to have to do here. We're not going to be able to value all of these payments at time 0 using just one annuity formula or notation. We're going to have to split up these payments into 2 sets so that we can use some nice annuity formulas and notations. And so keeping that in mind, where does it make the most sense to split up these payments? Well, I think it makes the most sense to split it up after time n plus 1. All right, we're going to have one set of payments here between time equals 2 and time equals n plus 1, and then we'll have a second set of payments that we will value from time t equals n plus 2 to forever. We're including all of those other payments in this second set of payments. Those are all going to be level payments of n dollars. But this series of payments here, you can see forms an arithmetic increasing progression. Every single payment increases by $1, and the initial payment is $1. So now that we have 2 sets of payments to work with, we can value each of them separately at time 0 and add those values together. So let's work on that now. Let's set up our equation. We'll have the present value of $104.92 is equal to these payments valued at time 0. Now let's start with the first set of payments here. Like I said, we have an arithmetic increasing progression here, and we're going to have an n number of those payments, right? This is the first payment and it's of $1. This is the second payment and it's of $2. Third payment is $3. Fourth payment is $4. So the nth payment is n dollars. So we have an n number of payments. So here's how we could represent the present value of these payments. We'll use our arithmetic increasing annuity immediate notation, which looks like this. We have IA and then n bracket the interest rate, which is 0.09. Okay, now the reason we're using this notation or this formula and not the present value for an arithmetic increasing perpetuity is because this is a finite set of payments. It does not go on forever. We have an initial payment of $1 and a final payment of n. This does not go on forever, right? We're cutting this off from the rest of the payments. So these n payments right here are not a perpetuity. They just form a regular arithmetic increasing annuity, all right? And so that's what we have right here. But now before we move on to valuing these payments at time 0, you have to ask yourself this question: does this notation or does this formula value these payments where we want them to be valued? And we want them to be valued at time 0, which is where this present value is valued. And whenever you use an annuity immediate notation or formula of any kind, an annuity immediate is always valued one period before the first payment. In this case, our first payment is made at time 2, so that means that this notation will value these payments at time 1, one period before that first payment. And that's not time 0, right? We want these payments to be valued at time 0, so in order to do that, we will need to bring this present value calculation back one more period. We need to multiply by a present value factor to the first power, right? Multiply by v. Now we're good. Now these payments will be valued at time 0. Okay, now one more thing before we move on. It's always good to check this as well. These payments are being made at the end of each year, so our period type is years, and the interest rate that we are using here is an annual effective interest rate, so everything matches up there. We have an n number of periods or an n number of years, and our interest rate is yearly. The frequency of the interest rate matches the payment cycle. And then one other thing to check here is the number that you're multiplying by this notation or this formula. In this case, we're not multiplying by anything, so we must be multiplying by 1, which makes sense because 1 is the amount of the initial payment, and it's the amount that every payment increases by. So this setup right here, this notation is good. This calculation here will value all of these payments at time 0 accurately. Now we're ready to move on to our second set of payments, which is going to be a lot easier to work with. We just have a payment of n dollars that is going to be made forever. All right, so we would calculate the present value of those payments using the formula for the present value of a regular perpetuity immediate. And that's as simple as taking the amount of the payment and dividing it by the interest rate, which is 0.09. Okay, once again, that interest rate is an annual effective interest rate, and our payments for this perpetuity are being made every year. So those two things match up. We have an annual payment cycle and an annual interest rate, so we're good there. But this will not value these payments at time 0, right? This calculation will value the present value of these payments one period before the first payment. Okay, this is the calculation for the present value of a perpetuity immediate. Whenever you're working with an annuity immediate formula of any kind, including perpetuities, the present value will be valued one period before that first payment. So this calculation will value these payments at time t equals n plus 1. That's not where we want them to be valued. We want them to be valued at time 0. So we need to bring that value back to time 0 by multiplying by a present value factor to the power of the number of years we need to bring it back, which will be n plus 1. All right, so we have v to the power of n plus 1. And now we're good. This will value all of those payments at time 0. And now we've completed our setup. This now represents how we would calculate the present value of this perpetuity, which we know what the present value is, but we don't know what that value of n is. So now our mission is to solve for n. And at first glance, it looks like that's going to be a nightmare, but I think you'll find that some nice things are going to happen in this calculation or in this expression that will make solving for n not too bad. Okay, and so let's work on that next. Let's talk about how we're going to solve for n. The first thing that I recommend that you do in a situation like this where it's not really clear how we're going to solve for that unknown variable is just write out all of the formulas for any notations that you have written down. So in particular, I'm talking about this formula right here for the present value of an arithmetic increasing annuity immediate. So if we write out what that is, we'll have 104.92 is equal to the present value of an annuity due for an n number of periods using the same interest rate, 0.09, and then we'll be subtracting n times v to the power of n, and then we divide by the interest rate, 0.09. Now that's still being multiplied by v, and then we're going to add that to this, and that's n divided by 0.09, and I'm actually going to split this up. And here's what I mean by that. We're going to have v to the power of n times v to the first power, right? You could split up this power by just writing it as v to the power of n times v, okay? Remember that when you multiply like bases, you add the exponents, right? If you had x squared times x cubed, that's equal to x to the fifth power. In the same way, v to the power of n times v to the first power is equal to v to the power of n plus 1. So we are allowed to do this, okay? Now, the reason I did that is because now you can see both of these terms have a common factor of v, and that's the same present value factor in each case. You would have 1 divided by 1 plus the interest rate, which is 0.09. So we have 1 divided by 1.09 in each case. Okay, so we could get rid of that by multiplying both sides of the equation by a factor of 1.09. That would cancel out with those present value factors. So I'm going to do that here, but I'll leave the original v notation there and instead just move right into that next step where we'll have 104.92 times 1.09, and then we can just remove those present value factors from this side of the equation, okay? So we'll have a double dot n bracket 0.09 minus n times v to the power of n divided by 0.09, and that is added to n times v to the power of n. I'm just going to move v to the power of n into the numerator there, and we'll have n times v to the power of n divided by 0.09. Now, what can we do next? Well, it looks like we have two fractions being added together that have a common denominator. They both have a denominator of 0.09. So we can add the numerators, and I think you'll quickly see that a very nice cancellation occurs. We have a negative n times v to the power of n, and a positive n times v to the power of n, right? So here's what happens here. We'll have 104.92 times 1.09 is equal to a double dot n bracket 0.09 minus n times v to the power of n plus n times v to the power of n divided by 0.09. Those two terms will cancel out in the numerator. We have a negative and positive version of the same term, and so now we just have 104.92 times 1.09 is equal to this annuity due notation divided by 0.09. So if we multiply both sides of the equation by 0.09, here's what we'll have. I'm just going to use one solid color from here on out. We'll have 104.92 times 1.09 times 0.09 is equal to a double dot n bracket 0.09. And now we have a much easier equation to manage in terms of solving for n. Having these four n's cancel out, right? This n, this n, this n, and this n, having those all cancel out is super nice because now there's only one n left in our equation. It's this n right here, and now we can work on solving for it. Okay, so always be on the lookout in these types of problems where you're solving for an unknown variable within an equation. Always look for spots in your equations where something nice might cancel out, like it did right here. All right, but now let's write out what this notation is equal to. Let's write out its formula. And by the way, if you multiply these three numbers together, you should get about 10.29 and some more decimals. But that will be equal to this notation, which is 1 minus v to the power of n divided by 1 minus v, right? That's the present value of an annuity due. Now, we want to isolate n in order to solve for it So I'm going to multiply both sides of the equation by 1 minus v to get it out of the denominator on this side. So we'll have 10.29 times 1 minus v is equal to 1 minus v to the power of n. And now what we can do is subtract 1 from both sides, as well as multiply 10.29 by 1 minus v. So let's work on that next. We're going to multiply 10.29 by 1 minus v, which, by the way, 1 minus v is 1 minus 1 divided by 1.09. And so I'll do that here as well. We have 1 divided by 1.09 to the power of n for this present value factor. Now, if you multiply 10.29 by this amount, or this quantity, you will get 0.84985 and some more decimals. Try to keep as many decimals as you can when you do these calculations. Try not to round off until the very end when you get to your final answer. But now what I want to do is subtract 1 from both sides of the equation. So we'll have that number minus 1, and that will be equal to negative 1 divided by 1.09 to the power of n. Now continuing up here, this decimal minus 1 will give you negative 0.150148 and some more decimals. And that's equal to the negative present value factor to the power of n. But now both sides are negative, so we can cancel out those negative signs. And what I'm also going to do in order to be able to solve for n is I'm going to take the reciprocal of both sides of the equation. I'm going to flip the numerator and denominator on this side, and then what that means is that this number, instead of being divided by 1, which it technically is right now, we're going to divide 1 by that number. We're going to flip the numerator and denominator. Okay, so if you take the reciprocal of both sides of the equation and cancel out those negative signs, here's what you'll get. You'll have 6.66 and some more decimals, and that will be equal to 1.09 to the power of n. And now we can finally solve for n by making use of a logarithm, right? We'll take the natural log of both sides of the equation, and we'll have the natural log of 6.66 and some more decimals, and that will be equal to the natural log of 1.09 to the power of n. But remember, the property of logarithms is that if you have the natural log of a to the power of b, that's equal to b times the natural log of a. You can move that exponent to the outside. So let's do that here. I'm going to rewrite this to be n times the natural log of 1.09. And so our final calculation is that n is equal to the natural log of 6.66 and some more decimals divided by the natural log of 1.09, right? You divide both sides by the natural log of 1.09 to isolate n and solve for it. And so if you plug this in your calculator, you should get that n is equal to 22. That is the final answer to this problem. All right, ultimately this was just an algebra problem, but it's the setup at the beginning of this problem that's usually the hardest part, right? How do you value all of those payments at time 0 correctly and then manipulate that equation or that expression such that you can solve for the unknown variable n? All right, so this was definitely a little bit higher up on the difficulty scale for these types of problems involving annuities. But if you understood the setup to this problem and you understood how we got to this solution, all the steps that we took algebraically, then that's a good sign. Okay, but with that, this was the last example for my Unit 2 review for financial mathematics on the valuation of annuities. However, I do have 5 more example problems for this Unit 2 review available exclusively on my membership site, JK Math Plus. So if that's something that sounds interesting to you, if you want some more practice, feel free to check that out. There's a lot more on the membership site than just unit review examples. So if you want to learn more about it, feel free to head on over to my website at jkmathematics.com/plus, and you can read all the details. Okay, but that's it for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, then that is it for now. So I will see you next time.